You ready? So they're okay, let's begin. Welcome to the University of Tennessee Nuclear Engineering Department Seminar Series. Before I introduce today's speaker, I have an award that I want to make. The university likes to recognize its long service employees, and we have one who's been with us, who's been with the university for 15 years, and I want to give him his service recognition today, which is a gift and a plaque, and the awardee is Gary Graves. Congratulations.
All this on tape, none are yet.
You started your applause before I told you a little bit about Gary. As everyone knows, he is our computer guru. He maintains and installs all of our computing equipment, and he and along with Dick Bailey are primarily responsible for the electronics and the equipment that we have to provide these webcasts. Our seminar webcast, and also our video conferencing that we do over the internet. Gary's primarily responsible for that. So let's give him another round of applause. Okay. Today's speaker is Mr. Ted Fox, who is the Director of the Engineering Technology Division at the Oak Ridge National Laboratory. Ted received his BS and MS degrees in Chemical Engineering from the University of Idaho. He's been with Oak Ridge for 26 years, and prior to that, he spent 4 years in the U.S. Navy. So it is indeed a pleasure for me to introduce Ted Fox. The title of his presentation is Nuclear Activities in ORNL's Engineering Technology Division. Ted, welcome.
Thank you. I have to confess that I've never done a PowerPoint presentation before. In fact, I was so pardon? Yeah, right. I believed in my abilities and your abilities to do this, so I brought my backup slides here just in case. Right. I've learned over the years. I was asked to talk to you about the nuclear activities in the Engineering Technology Division. Probably 10 years ago, I was probably be concerned whether today I would be able to talk about the nuclear activities in the Engineering Technology Division. But we were very upbeat about our what's happened in the last couple of years, and we'll get to that. I think that things are looking up for us. And now what I plan to do is tell you a little bit about what we are, who Engineering Technology Division was, and who we hope to become, and particularly the activities that relate to nuclear. Let me make sure I can use this thing here. See? In the beginning, around 1950, when you get back that far with the laboratory, because a lot of the organization charts were classified, it's hard to figure out exactly where everything came from. We struggled. So the early history is a little fuzzy. Actually, some of our recent history gets fuzzy too, but the early history was very fuzzy. But the origins of the division were from two separate organizations. One was the Experimental Engineering Division and the nuclear aircraft propulsion division of the laboratory. People tell me about the good old days, and I think that they must have been good old days, because it's hard for me to imagine working on nuclear aircraft propulsion with a straight face today. But times do change. But early on, we were the reactor people. We were the designers. We were the testers of reactors. The division was involved in all of the major reactors. Right after World War II, in the late 40s and 50s, there were some decisions made that were very important to the laboratory. One of them that was made was that argon would take the lead on light water reactors, which left Oak Ridge kind of out of that business. So Oak Ridge got involved in other aspects of light water reactors and into other areas. And so over the time, we have developed expertise in a lot of various reactors, particularly in research reactors. We were the first organization that designed the first research reactors. The materials test reactor that was built in Idaho was designed at Oak Ridge, and all testing was done there in our division. We designed, actually there was may have been at the university, there was a senior thesis, or maybe it was a graduate thesis on new reactor concept using the certain design of core, which Dick Cheverton did, and which became the high flux isotope reactor. That was designed in our division, and we led, a lot of the folks in our division led the construction and the operation of that facility. So we have a long history in building research reactors. Early in the 60s, we became involved in gas-cooled reactors. There was a large experimental program at the laboratory to build gas-cooled reactors which led to the experimental gas-cooled reactor, which some of you may have seen what's left there of it, the big dome building over where robotics is. At that time, they felt that the gas-cooled reactor was a safer option than light water reactors, and more efficient and more flexible, and a lot of people still believe that. We'll get to that in a little bit. Also at that time, we became involved in the molten salt reactor. We became involved over time with nuclear desalting, with different applications of high-temperature gas-cooled reactors using for process heating and so forth, and also became heavily involved in liquid metal reactors used for the breeder. Around 1978, 3 Mile Island gave us a number of new opportunities. Safety programs at the laboratory in our division took off. We became heavily involved with the Nuclear Regulatory Commission. At one point, I believe at that time, over 50%, probably 60% of the division's activities were for the NRC. Large experiments, a lot of analysis, a lot of data, a lot of consulting work with various organizations dealing with nuclear safety. Also at that same time, we began to, we did an important, I don't know how many of you know Truman Anderson, but he led an effort to do some strategic planning. And we decided that we ought to look at things other than nuclear for our long-term future, because maybe this isn't going to be long-term future. And so we began to do some other things. We started a fossil energy section. We got heavily involved in certain kinds of energy efficiency. At that point, around 1980, about 85% to 90% of our budget was nuclear. Today, it is about 20%, I would say, of our budget is nuclear. At the same time, there was a secret program at K-25, to study the use of a gas centrifuge for the separation for enrichment of uranium. Actually, I found in a textbook as early as 1952 that centrifuge enrichment of uranium was considered one of the two viable options, that and gaseous fusion. But in 1960, the U.S. got serious about that and started a program that I guess today would be considered kind of a black program, because the fact that they were even working on it was classified. And it remained heavily classified until the mid-'80s. Around 1986, I guess it was, 85, 86, they canceled the reason that we'll get to a little bit later. They canceled the gas centrifuge project. And laid off, there was some 900 to 1,000 people working on that. And there was a lot of technology that was developed from that, that was related to the gas centrifuge but could be applied to other things. And in some fit of wisdom, they decided to try to keep that technology. And they funded a group, I think at that time it was called the Uranium and I can't remember the name of the group, about 100 people they funded, which became the Applied Technology Division of the laboratory. This was around 86, that conversion was from 86 to around 1988. In 1993, that organization combined with the Engineering Technology Division, which currently existed, and we became another version of the Engineering Technology Division. And it was a very important influx of technology. They provided us with some interesting materials, power electronics, photonics, and other capabilities that we'd never had before at the laboratory and certainly didn't have in the division. Today we have, we are focused into four main areas. Those are my four section heads, Therese Stovall, Bob Schilling, Gary Mays, and Steve McNeely. The area under Gary Mays has the most majority of our nuclear work. Some of it was remnants from the NRC, but there is a number of, you can see the list there of the various items that we have expertise in our ongoing work, and there are some under engineering science where we do the pressure vessel and the thermal hydraulics. One of our unique strengths, even though the funding in this area has been hard to get, one of the fundamental strengths of our division is nuclear technical capability. We have a nuclear safety and operations analysis capability that came out of the NRC programs. We have a lot of experimental and analytical capabilities. And our current programs include the DOE Fissile Materials Disposition Program, some of the programs that continue with the Nuclear Regulatory Commission, a program with the Defense Threat Reduction Agency, which I won't go into today because it's fairly sensitive. We have a program on centrifuge enrichment of uranium. We have some advanced projects with NERI and space power, a new space power initiative that I'll talk about in a second. I guess it was a few months ago that Cheryl Green came here and talked to you about the plutonium disposition program. So I'm not going to go into a lot of detail here. Just want to tell you that this is a program that's in our division. The roots of this program come from a National Academy of Science study. They saw the real need to try to reduce the amount of weapons-grade plutonium in the world, particularly in Russia. And for whatever reason, the U.S. government picked up on this. I mean, they thought this was a pretty good idea. And so there is a significant program. The original study looked at three things. One was putting it in boreholes. One was vitrification, putting it in glass. The other one was to burn it in reactors. They threw away the borehole idea as not being viable. But they still are looking at both vitrification and, or some sort of form of just straight disposal and burning it in a reactor. This program is very important to us, to our division, because it is a well-funded program. It's allowed us to continue to keep a lot of expertise. We are at about $18 million this year, I believe, and we should hold steady at that for the next year or two. The idea is to take weapons and either process them, to either immobilize them or go through the fuel chain to convert it to some form of a waste that's self-protected. The program in the U.S. First starts off with plutonium conversion at Savannah River, where they make it into an oxide. Then there's a fuel testing aspect to it that the laboratory is involved in. This is a key role for the laboratory. Los Alamos prepares the fuel. We design the experiments, the field test experiments, we put the material in those experiments, and then have the experiments run out at the ATR at Idaho. We bring the material back here for analysis in our hot cells. The fuel design is being done by Duke, Kojima, and Stone and Webster. That's what DCS stands for. It's a conglomerate of consortium of nuclear companies that have got the contract with DOE to look at the fuel designs. The idea is to build a fuel fabrication plant in Savannah River, and then ultimately to burn it in two PWRs. And within the 2007-2022 time frame. But the real reason for doing the program is to try to stabilize the plutonium that's in Russia. And we have to have a balanced approach. We have to be doing it ourselves in order to encourage them to do it. But this is a very important part of the program, and it's very politically driven and very politically sensitive, and we don't know from one month to the next where it all stands. It's a very difficult program to quite get your hands around, because the Russians, although they're not all that interested in getting rid of the plutonium, they like to get the U.S. funding to work on it, but they see that as a natural resource. It's a wonderful resource for them. They want to use it as fuel. They never consider vitrifying it. That is just not on their horizon. But the idea there is to take a look at 4 options: light water reactors, one of the fast reactors, which turns out to be one of the near-term options that they have, gas-cooled reactors, which has been pushed by General Atomic. They've been working with them, and heavy water reactors, that particularly in Canada. Now, our role in the division is we lead the entire program that has to do with fuel. And we're involved in all these various aspects of both safety and fabrication and design. For all of those concepts that we were talking about, we actually lead the Russian activities. We have people over in Russia just about all the time, working with them, trying to encourage them to make progress. It's very difficult. There's a lot of cultural and technical reasons why they don't want to do things, and it's hard. It's a politically and socially difficult task. I want to just talk about one project that's real quickly. This is the Parallax project, and it's called Parallax because it's parallel with everything else. And this is the notion of burning the fuel in a CANDU reactor, which would be in Canada. And there's some good things about that, because it's being done in a third country. The Russians could ship their fuel there, we ship ours there, and the Canadians are in favor of it. Because I think they have a net revenue gainer there. The idea is for the U.S. and Russia to fabricate test elements, then the Canadians would irradiate it at Chalk River, laser, at Chalk River, and then we'd do some post-irradiation exams on the fuel, and the results, of course, would be reported to everybody. It's a very complex task to even get the fuel to Canada to test. Very difficult. These are some various photos of the moving the fuel from Moscow to Canada. We ended up renting a Russian Air Force plane to bring the fuel over, because it was the simplest way to do it. It's extremely difficult. The U.S. fuel was an interesting aspect of that, was that there was some demonstrators. We were planning on trucking the fuel to Chalk River in one of the protected vehicles like Y-12 has, but there was going to be some protesters in Michigan that were going to stop it, and so they put it in helicopters in Michigan and flew it to Chalk River, which really irritated the demonstrators. They got there. So this is a task that has a lot of elements other than the technical content, although there's a lot of interesting technical things there too. A part of that is to irradiate the materials, and I just thought I'd tell you about our ongoing materials irradiations that the division leads. This is probably the longest continuous experimental activity at the laboratory. It's something on the order of 45, 50 years. Colin West used to lead this. I don't know if you all know that. But we do irradiations in various reactors in HIFER. We do fusion materials irradiations for the U.S. and for the Japanese. We do materials irradiations in the Advanced Test Reactor in Idaho. And we use the Ford nuclear reactor, which is a very nice facility up there in Michigan, to do our very large pressure vessel irradiations. The HIFER, we can put it in various regions in the reactor, either near the core or out in the beryllium reflector. And this has been, we can have instrumented or uninstrumented capsules. We've had a whole variety of various materials, both for the fusion, for fuel irradiations for the HTGR program, and for a variety of other applications. This is a photograph of the radiation facility at the Ford reactor. We modified the facility now so that we don't have to build capsules. We can put the specimens in directly, remove them, and we don't have to replace the capsule itself every time. It's very nice because that's a lot of ways to take care of, so forth. So this is, and it's a lot less expensive. So it's become a very nice facility for us. The kind of things that we irradiate are coupons, large. In this case, it's a very large material that's typical of a reactor pressure vessel. For the past 40 years or so, we have been the NRC's go-to lab for reactor pressure vessels. We wrote the codes and standards for reactor pressure vessels, both to deal with structural mechanics and radiation damage. This slide here shows a special coupon that we devised, or test article. There was a few years ago, there was a notion that small flaws in the vessel would make the material tougher. And the test showed that, whoops, what have I done here? I skipped ahead several. Yeah. That shell of flaws would make the vessel tougher. Thus, they could extend the life of vessels longer. And is this where you? Now it's next one. Next one. Next one. That's good. We won't touch anything. But it turns out that that is only when you measure those properties in a uniaxial direction. If you measure it in a biaxial direction, that cancels out, and those flaws don't give you tougher material. This is a very important result because although it doesn't make the nuclear industry happier, it's an important safety determination. And this is the kind of work that our heavy section steel program has done. Over the years, this activity continues. We do both a lot of mechanical testing and a lot of irradiation testing. So it's a wide aspect of things. There are other NRC programs that I won't go into detail on that are kind of winding down in the area of operations analysis that we do for the NRC, looking at reactor incidents, looking at what causes those incidents. But the budget at the NRC has been declining over years, and frankly, it's not they're been a long-term customer, but they're not. There's not a lot of opportunities there. Okay, I want to talk about gas centrifuge for a moment. As I said, back in the 60s through 86, there was a large program here at Oak Ridge to develop a gas centrifuge. Let me first explain how the gas centrifuge works. Everybody knows, but obviously when you spin something fast, the heavy elements move to the outside. But what's interesting about this is the way a gas centrifuge for enrichment is designed is that you feed it in the center and then you heat it on one end. And because of natural circulation, you get a gradient of enrichment. And then you have a scoop at the top that removes the material. The capacity of a particular system is determined by the number of these machines that you stack either in series or in parallel. The interesting part about it is that the effectiveness of a gas centrifuge is dependent on really two things. One is how fast it's spinning, how tall it is. And the effectiveness, theoretically, is proportional to the velocity to the fourth power. So you can see that the faster you go, faster is really important. It's very important. And it's what's unique about Oak Ridge. Gives you a little bit of the history here. We began in 1960 development. It was interesting. I remember back in 1974, the Project Independence said that there was going to be 1,000 nuclear reactors by the year 2000. And so in order to fuel those reactors, you needed to have a lot of enrichment. So the plan was that we would have an advanced enrichment process on the order of 5 new 9 million SWU enrichment plants. That's a lot. I mean, Portsmouth is on the order of 5 million SWUs. So we're talking a big enterprise. There was essentially no competition at that time. There was low SWU cost was not considered to be an important thing. We were it was a monopoly. And frankly, fuel cost wasn't a big part of the cost of nuclear. The fuel is fairly small, so whether it cost, $60 a SWU or $80 a SWU really wasn't a big consideration. Well, what happened, though, was that we lost that monopoly, and there was a lot of competition. And also, at the same time, we had 3 Mile Island, and all of a sudden the demand went down. And at the same time, there was this AVLIS process that started up, which was Advanced Laser Isotope Separation. At that point, the U.S. government had spent $4 or $5 billion on gas centrifuge. They had 4 private companies competing. They were going full bore. They had built their own fiberglass factory, like Corning had. I mean, that was a $400 million factory that they built just to make fiberglass. It was a huge enterprise, and they needed to get out of it. They really did. They were just big enough. And so they decided to cancel this and focus on AVLIS. What's interesting, in 1999, U.S. Enrichment Corporation came to the lab and said, AVLIS won't work. We're interested in centrifuge. And so we said, okay, well, we can help you out. And so we started working with the U.S. Enrichment Corporation. Just to give you a little background, those early machines were designed for about 200 SWU per machine. They would cost about $50K per unit. And the original design was at about 10% of them would fail every year. And the cost of that was about $120 a SWU, which was not very good. So what's changed since then? Why do we think it's different now than it was then? Well, there is a lot of difference. A lot of things have happened in that last 16 years now. First, there's been improved low-weight, high-strength rotor materials, carbon fibers. The original machines were made out of fiberglass, and actually, at that time, that was classified. A lot of things have been declassified since then. A lot of information is now declassified. The glass wasn't as strong, it wasn't as good, there's a lot of things about it, and carbon fibers simply weren't available. You'd think that it would have been available for everyone, but they haven't been. Back in 1978, when they were designing it, they were not available. Not only carbon fibers available, but they're fairly inexpensive, and they're in abundant supply. So the materials, a whole different world for materials. Plus, there's existing commercial sources for these materials, and there's a lot of other advances in power electronics, motors, and so forth.
What is the typical spin speed?
Typical spin speed. Typical spin speed. Let's see, we went through that calculation. The exact one's classified. I could give you a ballpark number, but I can't remember off the top of my head. I'm sorry. It's fast, very fast. It's about, tens of thousands of RPM, hertz. There's some statistics here. Typical. Well, that didn't come out quite right. But Urenco is. I don't know if you're familiar with it, but that's kind of the benchmark. It's the European operating centrifuges. They're about 70 SWU per machine. They're typically about 16 feet tall. We don't know a lot, but we've got some intelligence, about a foot in diameter, and they're fairly low speed. What was put out in Portsmouth, Ohio, in the GSEP plant was about 200 SWU, as I said, about 40 feet tall and 2 feet in diameter, and they were what we consider intermediate speed. Current R&L design is for a 325 SWU machine, 35 to 40 feet long and high speed. If you could see the next a column, it would talk about what was the target that we were trying to get to back in the 70s, and it was 600 SWUs machine and very high speed and so forth. But we're not trying to do that anymore because we don't feel like we have to. We have a cooperative CRADA, a cooperative research and development agreement with the U.S. Enrichment Corporation. At the present time, it's about $4 million. Right after we signed this, this project has been just a fascinating project to be involved in. The DOE announced last November, I guess it was, the Secretary announced at Portsmouth that they were going to go forward with the gas centrifuge, that they're committing $276 million to it, and that it was going to be done in Oak Ridge. In fact, they sent us the money. Yeah, they sent us the money the day before George Bush was sworn into office, and then the next day we sent it back. So, so the big DOE program is still on the horizon. We don't know. The Department of Energy is still in favor of it, but there's a lot of work to do because of that political kind of fiasco that happens right in the January timeframe. But in the meantime, we are working with the U.S. Enrichment Corporation. Their funds into all their money, no DOE money, and our task is to ultimately to develop a commercial machine. At this point, what we're doing is testing some of the components, designing the machines, and we hope to, in the next year or so, to actually to operate a test machine at K25. Now, I'll show you some of that. And part of anybody's strategy would be to use the facilities at Portsmouth, Ohio. These facilities still exist. If you ever have a chance to go up and see them, you'd be amazed at what they're 30 acres under a roof. It is fantastic facilities that are in excellent shape. Right now, they're storing some waste in those buildings, but and the centrifuge is still there. Interesting. Centrifuges that they built are still there.
They're going to close.
No, they're going to. No, they're not going to close Portsmouth. They are. USEC is going to quit operating the fusion plant.
Okay.
Now, this is not owned by USEC. This is a separate part of that site, which is owned by the Department of Energy. But now they're using it for storage developments. But the facility is perfect for I mean, you could build a 3 million SWU plant there without having to build any infrastructure. It's excellent. Also, what it still exists, which is amazing, is at K25, all the test facilities still exist and are in excellent shape. In fact, the USEC has spent quite a bit of time and effort evaluating it and refurbishing some of it. And so we have, probably between what we have here in Oak Ridge and Portsmouth, a couple $100 million worth of investment that we can use immediately. So it's a very good deal. What we intend to do in Oak Ridge is to build the rotors here. And to build the machines here. to balance them, fabricate the sub-assemblies, and to test them. We have a fairly sophisticated testing facility there. Okay, moving on to the next thing is talk about some of our new initiatives. I don't know how you're familiar with NERI. It's the Nuclear Energy Research Initiative, which is a new DOE initiative that's been, I guess it started about 3 years ago, and we've received 2 of them, and I'll talk about both of them real briefly. One of them is to develop a solid-state reactor. With no, conceptually, it's a heat source that has no moving fluids, or could or couldn't. We don't know. But what the idea is to use some of the new materials to develop conceptually a new kind of a reactor source that would be inherently safe. Particularly graphite foams is what really brought this about. I don't know if you knew about the new invention at Oak Ridge, but this graphite foam is a fantastic material, and I'll tell a bit more about that. The research would include materials research, neutronics analysis, simulation and prototyping, and then an assessment of its commercial viability. The graphite foam is interesting. It was actually, like most great inventions were mistakes. They're trying to do something else, and they screwed up and made this. But what's neat about it is it has tremendous thermal conductivity. It's estimated to be about 1,500 watts per meter degree Kelvin, and the overall thermal conductivity is about 180. So it's on the order of copper. I mean, if you haven't seen this, afterwards, I'll come down and I'll give you a little demonstration of this stuff. It's pretty neat stuff. But the idea is to use that and to embed fuel in it in some form. Embed fuel in it, because the heat transfer is just amazing with this. And done a lot of calculations, and it looks like it's feasible. We built a little prototype to do some measurements with an electrical heat source to see what kind of thermal conductivity it would have and whether or not it could handle the heat load and so forth. We're about in the middle of the project. This is pretty way out. This is neat stuff. This is really way out. It's pretty exciting. And we're going to, by the time we get finished, we'll publish a report that will talk about the feasibility of doing these things and our experimental results, and then a very crude assessment of commercial viability. One other activity that we have with NERI is it's related to advanced monitoring of equipment, and Dell, you would appreciate this. This is using our nonlinear dynamic capabilities, chaos theory, for predicting the failure of machinery. And this has just begun. We've had some success in other areas, and DOE liked the proposal, so we just began. I'd like to finish up with the last two things. One is talk about some of the spin-offs of the nuclear works that we've done, which is pretty interesting. Back in the early mid-'80s, we became very expert in looking at various forms of sphere accidents of reactors. Sphere accident analysis is a strength, and there are a lot of activities for the NRC in sphere accidents. And one of the elements of sphere accidents that concern you were steam explosions. And we had a lot of analysis that we did concerning steam explosions, and we developed a lot of expertise. We've been able to use this expertise to attack two different problems. One is in the metals business, particularly aluminum smelting and so forth. They have a lot of steam explosions. They occasionally don't like to have them, but they have them, and they kill people, and they hurt people, and they blow up buildings, and they're pretty spectacular when they happen. What they've done in the past is to coat their pits and so forth with materials that they didn't know how it worked, but they knew that if they put certain kinds of organic materials on their pits, that seemed to keep the steam explosions from occurring, and they would test it. It was a really an Edisonian approach to dealing with this problem. And there was no fundamental underlying understanding of the phenomenon. We were able to understand that phenomenon and devise a technique for them that doesn't involve these materials, because these materials can be outlawed by the EPA, which is a real problem for them. And it turns out that if there's air in the water, something to cushion it, the steam explosion doesn't occur. And so the whole thing, and that's what these materials were doing. They were outgassing, and they were providing that cushion for them. And so this has been a very nice piece of work that that we've done at the lab. Another, this was headed up by Lucy Kelly-Harkin. I don't know if you all know Lucy, but he's been heavily involved in this. Another thing that he discovered how to do was how to make steam explosions occur on a very small scale, which had never been done before, and very easily. And so he devised a technique of being able to have a steam explosion propellant, which in this case is about the size of a shotgun shell, although we have in our building ones that are the size of a 40-millimeter gun now. And it's right below my office. And it's on the order of I think it's 2 or 3 times the energetic power of conventional TNT or RDX or any of that explosive. And the nice thing about a steam explosion is that it's a longer duration, so you don't get as much shock, and you can actually propel things better. So it's got a lot of interest to the Defense Department. And we've got some good funding now from the Defense Department for looking for this, but all an outgrowth from our nuclear work. The last thing I would talk about is another brand new start, and that's our work with DOE on space nuclear. This has been stop and start over the years. We've been involved with them before on this. They're interested in helping, DOE and NASA are combined, trying to find energy sources for the long missions, for Mars, for long-term missions. And they're looking for terrestrial systems and also systems for propulsion. And our role at this point is to be the evaluator. And that concludes my prepared comments.
Okay. Now, do you have any questions or comments for Ted?
Did you pick up from K-25 the spin tests?
We picked up the spin test facilities and moved them to Y-12, and now we've moved them back to K-25. Yes, we still. In fact, it's interesting. There was some 30,000 classified pieces of parts, equipment, and stuff. It's all still there. I'll tell you, they haven't done a very good job throwing stuff away over there, because it's all still there. We were also able to find almost all of the classified reports and documents. And there's still, I estimate, about 100 people at the lab that have been involved in centrifuge. So there's still a lot of centrifuge knowledge at the laboratory.
Any flywheel tests at Star Wars?
We had the capability. I hadn't heard anybody interested in it. Although, there's a little bit of interest in part of NASA. I mean, not Star Wars, but in some flywheel space work.
You had a question?
Yes, sir.
About 2 or 3 weeks ago, DOE asked me to talk to the committee that was looking at the 3 university research reactors in Cured Michigan that the DOE fears will be closed down in the next 7 months.
Don't close Michigan.
I was going to say, if that were to happen, is there any place else that you can do those large diesel tests?
I think there is, but there's no place better. We talked about this once before. I don't remember the answer to that. I know there is overseas. Yeah.
Yes.
I know there is overseas, but I thought there was one other here, but I don't know the answer to that.
That
Sure.
big ORR.
Yeah, I know. Yeah, I know.
Well, there's the NC State research reactor. NC State, which I think is 5 megawatts. And then there's University of Missouri, which is 10 megawatts.
Right.
The Michigan reactor, the ORR tower, it's a big flat face.
Okay, put things up next to it. Yeah.
I don't know the answer to that.
Any other questions or comments? Okay, let's express our appreciation to Ken. We do have refreshments down on the second floor, and everyone is invited. Thank you.
Does anybody want to see this stuff?
Yeah,
I brought some ice. There has some ice. Yes, put it on your hand.
Gary, leave it on. Melting.
Just wait.
Yeah, in such a way that what's going to happen? It's cold. Yeah, I can feel it.